Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Raw foundation models are remarkably capable, yet inherently unfocused. They contain vast amounts of general linguistic knowledge, but out of the box, they lack the structural precision required for enterprise applications. This diagram shows the domain gap, the friction point where the chaotic web of general pre-training data fails to meet the rigid execution demands of specialized business workflows. Bridging this requires a staged strategy, transitioning the model into structured environments like legal or healthcare records. You can identify a domain gap through several clear symptoms: failing to recognize proprietary terminology, misunderstand novel user intents, or break required regulatory document structures. Deploying a raw model directly into an enterprise pipeline without systematic adaptation invites operational failure. It directly increases the likelihood of severe hallucinations and compromises data compliance. This matrix shows the diagnostic framework. Exhaust simple context optimization on the vertical axis before altering model weights on the horizontal axis. Diagnose first. Is it a knowledge or behavior gap? A knowledge gap leads to RAG. A behavioral gap dictates supervised fine-tuning. By rigorously diagnosing the exact nature of the failure up front, engineering teams avoid burning multi-million-dollar compute budgets on structural problems that could be solved by simply injecting better context. This graphic breaks down the rent versus buy economic trade-off of prompt engineering. Prompting acts like a mortgage, where you are paying per inference. While writing a prompt is fast and allows for rapid iteration, increasing the length of that prompt permanently spikes the compute cost for every single user request over the entire lifespan of application. This diagram outlines RAG. It grounds answers in proprietary data by retrieving documents before generating a response, avoiding modifying base model weights. Semantic kernels orchestrate this. They chain functions, managing live database lookups and API calls to feed precise data directly into the generator model. RAG introduces two specific vulnerabilities. First, if the retrieval module fails to find the right data, the model will hallucinate. Second, feeding live external documents creates an attack vector for prompt injection, where malicious instructions hidden in the retrieved text can hijack the model. Optimizing context provides a highly agile, low-cost baseline, but it hits a hard mathematical ceiling when the application requires permanent changes to the model's fundamental reasoning, behavioral tone, or output schema. This illustration shows the supervised fine-tuning pipeline, or SFT. You escalate to SFT when prompts consistently fail to deliver rigid structural formatting, like precise XML outputs, or when you need specialized multi-step workflows and nuanced domain terminology. Full supervised fine-tuning comes with severe constraints. Modifying every weight in a massive neural network requires direct access to the model architecture, massive upfront hardware investments, and introduces strict data privacy and governance liabilities. This diagram illustrates PEFT. These mathematical shortcuts bypass compute constraints, allowing model training without a hyperscale data center. The most common method is LoRA. It freezes massive original parameter matrices and trains tiny secondary update matrices, radically reducing memory usage while allowing customized behaviors. An even leaner iteration is QLoRA. QLoRA stands for Quantized Low-Rank Adaptation, a method that crushes the base model's precision down to 4-bit integers, making it possible to tune multi-billion parameter models on standard, commercially available consumer hardware. Utilizing these parameter-efficient techniques, highly specialized bespoke enterprise agents become financially viable for smaller engineering teams. Once a model is structurally accurate, it must be aligned. Preference optimization is required to enforce strict organizational policies, ensure safety expectations are met, and match subjective human values in the output text. This comparison charts the evolution of alignment techniques. The traditional pipeline, RLHF, or reinforcement learning from human feedback, requires training an entirely separate reward model to map complex human preferences, demanding heavy computational overhead. Direct preference optimization, or DPO, simplifies this pipeline entirely. DPO optimizes the language model directly on pairs of chosen versus rejected responses, eliminating the need for a secondary reward model and vastly streamlining the alignment process. To maintain natural variance in the output, engineers often employ soft actor critic, or SAC. SAC is an algorithm that balances exploitation of known good answers with exploration, preventing the aligned model from collapsing into highly predictable, repetitive robotic text. True alignment bridges the gap between raw statistical probability and human-centric safety. It ensures the system behaves reliably, even when navigating highly subjective or ambiguous edge cases. This diagram shows architectural ensembling. Ensembling is the practice of combining multiple specialized models so that a secondary logic layer, or meta-model, can evaluate their outputs, balancing individual weaknesses and severely limiting the chance of a hallucination. Scaling up specialized performance presents a physical problem. Simply making a single, monolithic model larger to handle more complex tasks drastically increases inference latency and operational compute costs. This schematic details a mixture of experts, or MOE, architecture. MOE creates specialized subnetworks inside one giant model, using a gating network to calculate probabilities and activate only a few select expert neural networks per token, scaling the parameter count without scaling the compute load. The critical challenge when training an MOE is preventing expert collapse. Expert collapse occurs when the gating system funnels too many tokens to just a few experts, causing memory overflow bottlenecks while the specialized capacity of the other experts goes entirely wasted. Advanced enterprise deployments prove that sheer model size matters less than intelligent routing. Dividing computational labor among specialized experts yields faster, more robust results. When deploying to resource-constrained edge environments, hardware limitations force the use of model compression. This involves KV caching, which stores pre-computed attention tensors to speed up generation, and pruning, which systematically removes unimportant weights to reduce computational complexity. This graphic demonstrates distillation. Model distillation is a training process where a massive, capable teacher model is used to train a smaller student model, forcing the student to precisely replicate the outputs and logic of the teacher while maintaining a fraction of the memory footprint. This chart visualizes the chinchilla paradigm. The chinchilla paradigm challenges the industry trend of endlessly building larger models by proving that models become severely undertrained and inefficient if the training data volume does not scale proportionally with the parameter count. In real-world deployments, efficiency always beats raw scale. A smaller, highly optimized model trained on vast amounts of high-quality data will consistently outperform a massive, undertrained monolith on a fixed compute budget. This diagram illustrates the LLM ops feedback loop and the reality of domain shift. Once live, the environment drifts as it encounters new terminology, regulatory changes, and adversarial prompt patterns, all of which degrade model performance. To combat domain shift, you must maintain a continuous operational loop. This requires rigorous online monitoring, tracking live task success rates, user feedback, and retrieval relevance to detect exactly when the model begins to fail. This checklist summarizes the full spectrum of the adaptation strategy. You must continually match the specific failure to the correct method, balancing the exact data requirements against the core operational risks of prompting, RAG, or fine-tuning. Operational success depends on systematically applying the least invasive intervention required to turn general statistical potential into reliable, specialized execution.